Hello everyone, this is K. Nagaraju, contract lecturer in Electronics and Communication Engineering from Government Polytechnic for Women Nizamabad, from the Department of Technical Education, Telangana. Today I am going to explain one of the important topic in the AC bridges, that is the Maxwell's bridge, and also small introductory about the Hales bridge also. Generally, in a previous class, we already discussed about the Wheatstone bridge. With the help of Wheatstone bridge, we are measuring the unknown resistance in the bridge circuits. After then, we have one more important bridge circuit is the Maxwell's bridge. Here, on the completion, that means the main objectives of this presentation is understand the Maxwell's bridge circuit, measure inductance using the Maxwell's bridge, and the limitations of the Maxwell's bridge. On the completion of this period, you will able to know the understand the Maxwell's bridge circuit and measure the inductance using the Maxwell's bridge. That means with the help of this particular Maxwell's bridge, we are measuring the inductance and what are the limitations of the Maxwell's bridge, and also small introductory about the Hales bridge. In the previous class, we already discussed about this particular Wheatstone bridge and also measure the unknown resistance, and also we are drawing the Thevenin's equivalent circuit of the Wheatstone bridge. In the networks, we are having the different types of theorems like a superposition theorem and maximum power transfer theorem, Thevenin's theorem and Norton's theorem. In this particular Wheatstone bridge, what we have to do, the total bridge circuit can be modified in the form of Thevenin's equivalent circuit. That means the multiple energy sources can be replaced with the equivalent circuit. That means if the circuit is bulk, that means the more number of energy sources and more number of resistance is present, then if you want to find out the load response or the load power, then we are using the Thevenin's equivalent circuit. With the help of this particular Thevenin's equivalent circuit, the load terminal, where the load terminal is present, the load terminal can be converted, that is open circuited, and calculated the voltage across the load terminal. The voltage is called the Thevenin's voltage, and across these load terminals, the voltage source are replaced with their internal impedance. Like voltage source is replaced with the open circuit, the current source open circuit, the current source replaced with the open circuit. That means they are matched with their internal impedances, then finding the total equivalent resistance in the terminals of the load. Then first we are measuring the Thevenin's voltage, second we are measuring the total equivalent resistance. These two are connected in series. Then what we are replacing, the load is connected to the circuit, then we are forming the one series circuit, the Thevenin's equivalent voltage in series with the Thevenin's equivalent resistance and the load terminal. That means the entire circuit is replaced with um, two elements only. That means the Thevenin's equivalent voltage and Thevenin's equivalent resistance. This is called as generally the Thevenin's equivalent circuit of the any bridge circuits or the any electrical circuits. Here our main topic is the Maxwell's bridge. What is the use of this particular Maxwell's bridge? The name itself is invented by the scientist Maxwell. And also, this particular scientist, we discussed in the electromagnetic theory also the Maxwell's equations, the four Maxwell equations. The Maxwell equations are derived from the conductor, derived from the free space, derived from the dielectric materials, based on Gauss law, based on Ampere circuits law, based on Faraday's law. The Maxwell invented the Maxwell designed the four Maxwell's equations. Here also, this Maxwell's is invented the this particular Maxwell's bridge circuit. With the help of Maxwell's inductance bridge, is a basic bridge circuit, because of this is used to measure the unknown inductance. The unknown inductance can be measured with the help of Maxwell's bridge. And here it measures an unknown inductance by comparing it with a known inductance or the standard inductance. It measures an unknown inductance by comparing it with a known inductance or the standard inductance. That means is nothing but a comparison. That means in this particular bridge circuit we are having the four arms. The three arms are is the known parameters or the known quantities, and remaining is the one quantity, unknown quantity. Then we are if the circuit is bridged, circuit is balanced, then we are automatically we are having the some ratio relation, then we are finding the unknown quantity or the unknown parameter. Here we are what we have to do in the Maxwell's bridge, it measures the unknown inductance by comparing it with a known inductance or the standard inductance. And the four ohms and four impedances, in these three known and one is the unknown impedance. I already said that in the four ohms, the four impedances, the total four, one is the unknown quantity or the unknown impedance, and the remaining three are the known impedances. With the help of comparison, we are easily finding the unknown quantity of the bridge circuit. And also we are using the AC power supply and detector in this particular Maxwell's bridge. And here the Maxwell's bridge is used to measure the unknown inductance in terms of the known capacitance also. And one of the ratio arm has a resistance and capacitance in parallel. We already discussed the bridge which having the four arms, one of the arm which having the resistance in parallel with the capacitance. That means for example, if you are taking the first arm resistance R1, the first arm capacitance C1, these two are connected in the parallel manner. Like already we are having the circuit diagram, the first arm resistor in parallel with the capacitor. This is the first arm, that is the resistor R1, capacitor C1. That is, one of the ratio arms has a resistance and capacitance in parallel, that is the R1 and C1. The other ratio arm has a fixed resistance. Other is the fixed resistance, that is the R2. That is the R2. And the third arm has variable resistance. The third arm is the variable resistance for balancing the bridge. For balancing the bridge, we are having the resistor R3. And remaining one is the unknown impedance is connected to the final arm. That means what we have to observe in this particular construction part of the Maxwell's bridge, the Maxwell's bridge having the four arms, the first arm which having the resistance in parallel with the capacitance. The second arm is the fixed resistance, and the third arm is the variable resistance for balancing the bridge circuit. The fourth arm is the unknown inductance. That means we are constructed the bridge with the help of these four arms. That is the construction part of the Maxwell's bridge. And in general, the equation of the bridge circuit, before going to equation part, you must know the circuitry. Here we are having the Maxwell's bridge. In the Maxwell's bridge, we have to observe the resistor, the first arm. Here the first arm, this is the first arm. The first arm, we are connected resistor R1 in parallel with the C1. This is the first arm. And the second arm is the fixed resistor, that is the R2. And the third arm is the variable resistor. For balancing of the circuit, we are connected the resistor R3. And fourth arm is the variable impedance. Here we are not connected the pure resistors or the pure end, because of this is the AC bridge. That means which having the impedance which having the resistive part as well as the reactance part. That is the, here we are having the resistor Rx and Lx. This is the impedance, that is the Z4. That means here the arms are like, this is the Z1 arm, this is the Z2 arm, this is the Z3 arm, this is the Z4 arm. The four arms are connected in the form of bridge, and we are connected the detector at the balancing of the bridge circuit. These are connected across, that means the supply is given to this particular bridge circuit with the help of energy, that is the AC supply. This is the construction of the Maxwell's bridge. In the Maxwell's bridge, we are having the four arms. The four arms are connected in the diamond shape. Like here, the bridge circuit, we are having the four impedances. The four impedances, three are known impedances and one is the unknown impedance. The first impedance, that is the known impedance. The known impedance, we are having the two components, that is the resistor and capacitor. These two are connected in parallel. And second arm impedance is Z2. Z2 is equal to the resistance is the fixed resistance, that is the R2. The third impedance is the Z3. The resistance, the Z3 is nothing but here R3. That is the resistance R3 is the variable resistance. For balancing of the circuit, we are using the third impedance is the R3. And fourth is the unknown impedance. It consisting of resistive part and as well as the reactance part, that is the Rx into Lx. These are connected to the supply, and the balancing we are using the detector. This is the construction about the circuit diagram of the Maxwell's bridge. Here, in general, the general equation for the Maxwell's bridge is Z1 Z4 is equal to Z2 into Z3, because of the circuit is balanced, the bridge is balanced. The bridge is balanced, then Z1, this is the Z1, this is the Z2, Z3 and Z4. Already we know if the circuit is balanced, then Z1 Z4 is equal to Z2 and Z3. Z2 and Z3. That is the balancing equation of the bridge circuit. The balancing equation of the bridge circuit, that is Z1 Z4 is equal to Z2 Z3. These are the impedances. Then applying here, this becomes, that means Zx, because of here Z4 is the unknown. Then we are replaced with Z4 to Zx, then Zx is equal to Z2 Z3 into 1 by Z1. This is the LHS part is multiplied to the RHS. Then we are getting the Zx is equal to Z2 Z3 into 1 by Z1. 1 by z1 is nothing but admittance of the first arm. Then replace it with 1 by z1 is equal to y1. That is, here the equation becomes zx is equal to z2 z3 into y1, because of y1 is equal to 1 by z1. The impedance and admittance both are inversely proportional to each other. Then zx is equal to z2 z3 into y1. And here y1 is the admittance of arm 1. Y1 is the admittance of the arm 1. And this is the bridge circuit. According to the figure, we are already assigned the values of the four arms. Like here, z2 is equal to R2. That is the second arm impedance is the fixed resistance, that is the z2 is equal to R2. Z2 is equal to R2. Second one is the Z3 is equal to R3, because of Z3 is equal to R3 is the variable resistance, but here for generation of the equation we are taken as the fixed quantity, like a fixed quantity. That means here the R3 is the variable, but for calculating the unknown inductance, then we are taken as the fixed is the R3. And third one is the admittance y1. In the admittance y1, here I am clearly explaining y1. Here we are having the two arms are connected in parallel, like here resistor and in parallel with the capacitor. This is the resistor R1, here capacitor C1. You have to write the admittance. Then the admittance here y1 is equal to generally in the impedances, if the two arms are connected in series, then we are writing as R1 plus j omega C1. Here we are taking the admittance, then 1 by in the form of series, because of these two are parallel, but here we are measuring the admittance. Then the parallel is converted into series is converted into parallel in the admittance manner. In the in a general impedance, the series connection is a series, the parallel connection is parallel connection, but admittance is the series is parallel is series. Then y1 is equal to y1 by r1 plus 1 by j omega c1. 1 by j omega c1, that is the part. Then finally y1 is equal to 1 by r1 plus j omega c is again going to the numerator. That means we are getting the total y1 is equal to the admittance of the first arm. Y1 is equal to 1 by R1 plus j omega C1. This is the numerator part. Here R1 is the denominator part. This is the admittance of first arm. Then substitute the values of, here we are getting the y1 is equal to 1 by r1 plus j omega c1. The substitute the values in the equation 2. That means the starting equation is the z2 z4. In place of z4 we are replacing with the zx, that is the zx is equal to z1 z2. Again zx is equal to z2 z3 into y1. Then zx is equal to z2. Zx can be replaced with their impedance part, that is the resistive part, and reactance part, that is the Rx plus j omega Lx. Zx is equal to Rx plus j omega Lx is equal to Z2 Z3. Z2 is nothing but R2, Z3 is nothing but R3 into Y1. Y1 is equal to 1 by R1 plus j omega C1. Here j omega C1 is the numerator part, not a denominator. Here 1 by, clearly observe, 1 by R1 plus j omega C1. J omega C1. Then multiplied with R2 and R3. R2 and R3. Then separate the real and imaginary terms. Then separate the real and imaginary terms, that is Rx is equal to here clearly observe that separate the real and imaginary terms. Here we are having the Rx plus j omega Lx. I am taking the here I am clearly explaining Rx plus j omega Lx is equal to R2 R3 into 1 by R1 plus j omega C1. Then multiply the these terms R2 and R3, that is the R2 R3 divided by R1 plus R2 R3 into j omega C1. Here this is the real part, this is the imaginary part. Here also the Rx is the real part and j omega Lx is the imaginary part. Here based on this we have to observe the real, separate the real and imaginary terms. Then we separate the real and Rx is equal to R2 R3 into 1 by R1. Then finally we are getting the Rx is equal to R2 R3 divided by R1. This is the real part. And imaginary part here j omega cancel, then Lx is equal to R2 R3 into C1. That means we have to measure the unknown inductance Z4 is equal to, or Zx is equal to Rx plus j omega Lx. Here we know we are find out the Rx with the ratio of R2 R3 by R1. These are the known parameters, and Lx is equal to R3 R2 R3 and C1. These are also known parameters. That means with the help of known parameters we are finding the unknown parameter. Then we are finally finding the impedance of the circuit. This is the calculation or the finding the unknown inductance in the Maxwell circuit. That is Rx is equal to R2 R3 divided by R1 and Lx is equal to R2 R3 into C1. Here the all parameters are is the known parameters in the RHS side, and LHS side the unknown parameters. In this way we are calculated the unknown inductance in the circuit. This is the equation part of the Maxwell's bridge. And the limitations of the Maxwell's bridge. Again, I am showing the circuit and discuss about the Maxwell's equation in the speed manner. Here, the Maxwell's bridge construction, we are using the four arms. The four arms are connected in the bridge manner. The first arm is the known impedance. The second arm also is the known impedance. And third arm also known impedance. And fourth arm is the unknown impedance. In the first arm, the resistor and the capacitors are connected in a parallel. That is the first arm. That is the R1 and C1. R1 and C1 are connected in the parallel. And the second resistor is the second impedance is the fixed resistance, that is the R2. Third impedance is the not a fixed resistance, is the variable resistance, the variable resistance for balancing of the circuit. The fourth one is the unknown impedance. This is the unknown impedance, these are the known impedances. With the help of known impedances, we are finding the unknown impedance with the help of Maxwell's bridge. In the equation part, what we have to observe here, Z2 is equal to R2 because of the Z2 impedance is the fixed resistance, that is the R2. The Z3 is the R3, this is the variable resistance. If the circuit is balanced, then we are directly taken as a Z3 is equal to R3. And Z1 is the impedance, but here we are cross multiplying the equation, then we are observing the Y1 impedance, that is the impedance Y1 is equal to 1 by R1 plus J omega C1 is the admittance of the first arm. Substitute these all parameters in the equation, that is the main equation, then we are getting the Zx is equal to Rx plus j omega Lx is equal to R2 R3 into 1 by R1 plus j omega C1. Here separate the real and imaginary terms, then we are getting the unknown resistance and unknown inductance, that is the unknown impedance, that is the Rx is equal to R2 into R3 divided by R1 and Lx is equal to R2 R3 into C1. That is the measurement of inductance using the Maxwell's bridge. And the limitations of the Maxwell's bridge. The Maxwell is limited to the measurement of inductance of the medium quality factor coils, that is the between the range of 1 to 10, that is the 1 less than q less than 10. Generally, the quality factor the quality factor is the ratio of the voltage across the capacitor or inductor to applied voltage, or the voltage across the inductor to our applied voltage, or the maximum stored energy per cycle to maximum energy dissipated cycle is nothing but a quality factor. That means is the how much amount of loss, that is the dissipation, to how much amount of energy is stored. The ratio can be represent the quality factor. Here the Maxwell is limited to the measurement of inductance of the medium quality factor coils, that is the Q coils. The phase angles of the resistive elements in the arm 2 and arm 3 add up to 0 degrees. The phase angles of the resistive elements R2, that is the fixed resistance, and R3 is the unknown impedance. Here also we are having the resistive element. These two angles are added up to 0 degrees. The sum of the angles of R1, that is the arm 1, and arm 4, that is the known impedance, and the variable impedance, that is the R4, must also add up to 0 degrees. That means here the limitation of the Maxwell bridge, one more important point is the phase angles of the resistive elements in the arm 2 and arm 3 add up to 0 degrees. The sum of angles of arm 1 and arm 4 must also add up to 0 degrees. And the phase angles of quality high coil will be very nearly 90 degrees positive, which requires that the phase angles of the capacitive arm must also very nearly 90 degrees is the negative. the phase angles of high Q coil will be very nearly 90 degrees positive, which requires that the phase angles of the capacitive arm must also very nearly 90 degrees negative. 90 degrees negative. Then the Maxwell's bridge is unsuited for measurement of inductance of coil with a low quality factor coils. Like if the circuit having the low quality factor Q is less than 1, we are unable to, that means we are not suited for the measurement of the inductance. For balancing of the Maxwell's bridge, first adjust the R3 for inductive balance and then adjust the Rn, R1 for resistive balance. Already discussed this particular point. The resistance R3 is used for variable resistance and balancing the bridge circuit. Here, for balancing the Maxwell's bridge, first adjust the R3, that means the resistance R3 adjusted for inductive balance, and then adjust the R1 for resistive balance. This is the limitations of the Maxwell's bridge. These are the limitations of the next one is the Hale's bridge. Used to measure the resistance and inductance where resistance is a small fraction of the reactance and used for coil with a high quality factor, used in measurement of incremental inductance, not used for coils whose quality factor is less than 10. The Hale's bridge also used for measuring the inductance based on the quality factor of the circuit. With the less than 10, we are not using the Hale's bridge. If the high coil of the quality factor of the circuit, then we are using the Hale's bridge. This is the discussion about the Hale's bridge. In this particular topic, we already discussed about the Maxwell's bridge, the measurement of unknown inductance and the limitations of the Maxwell's bridge, and the small introductory about the Hale's bridge. Here we are having the few important questions are the in the competitive examinations maximum they are asking the some uh, typical questions in the examinations. Here we are discussed with the help of quiz questions. The Maxwell's bridge is used to measure the unknown resistance measurement, capacitance measurement, and inductive measurements, or none of this. Our answer is the Maxwell's bridge is used to measure the unknown inductive measurement. Inductive measurement. The Maxwell's bridge is suited to measure the dash medium quality factor coils, the high quality factor coils, and low quality factor coils, and none of the above. Actually, our answer is high quality factor coil and also medium quality coils also. And here, the Maxwell's inductance capacitance bridge can be used for measurement of the inductance. The Maxwell's inductance capacitance bridge can be used for measurement of the inductance. Here also we are having some small explanation about this particular question. A Maxwell's inductance capacitance bridge is used for measurement of the inductance by making comparison with the standard capacitance value, and the voltmeter is used to measure the voltage while an ammeter is used to measure the current. Okay, that is the explanation is a Maxwell inductance capacitance bridge is used for measurement of inductance by making the comparison with the standard capacitance value. Voltmeter is used to measure the voltage while an ammeter is used to measure the current. This is the important discussion. And The balance equation for computing the value of unknown inductance is, we already derived this particular equation, that is the Lx is equal to R2 R3 into C1. Here, the balance equation for computing the value of the unknown inductance is Lx is equal to R2 R3 into C1. Here explanation is, the balance equation for determining the value of unknown inductance is given by the relation Lx is equal to R2 R3 into C1, where C1 is the capacitance across the resistance R1 and R3 is the variable resistance and R2 is the fixed resistance. This is the balance equation for computing the inductance, that is the Lx is equal to R2 R3 into C1. The standard inductance requires no shielding, that is true or false. That is the false, because of the standard inductor requires the shielding, but here they are giving the no shielding. That's why our answer is false. Explanation: the stray magnetic fields are present in a circuit consisting of inductances and capacitances. In order to eliminate the stray magnetic fields, the proper shielding is required for the standard inductance. The standard inductance requires the shielding. That is, the stray magnetic fields are present in the circuit consisting of inductances and capacitances. That is the requirement of shielding of the standard inductor. That is, the stray magnetic fields are present in the circuit consisting of inductances and capacitances. In order to eliminate the stray magnetic fields, the proper shielding is required for the standard inductance. The standard inductance provides the rated inductance directly. Is a false, because when the current flow through the standard inductance is adjusted precisely, it provides its rated value of inductance. That's why the standard inductor provides the rating inductance is directly is the false. And what is the significance of capacitors in a Maxwell's bridge? What is the significance of capacitors in a Maxwell's bridge? They are cheap. What is the significance of capacitors in the Maxwell's bridge is they are in the cheap. That's why in a Maxwell's inductance capacitance bridge, the capacitors are cheaper when compared to the stable and accurate standard value of inductors. And one more question is the bridge balance equation can be written in impedance form, resistance form, conductance form, and admittance form. Our answer is admittance form. Explanation is, the bridge balance equation for the Maxwell's inductance capacitance bridge consists of admittances. This is due to connection of the capacitance in parallel across the resistance 1 of the ohm ratio. In the circuit, it shows the resistor R1 and C1 are connected in parallel. That's why the bridge balance equation in the form of admittance form. The bridge balance equation for a Maxwell's inductance and capacitance bridge consisting of admittances. This is due to connection of the capacitance in parallel across the resistance in 1 of the ohm ratio, that is the form ohm 1. In this frequently asked questions in the examination, draw the circuit of Maxwell's bridge and determine the unknown inductance value in terms of the known capacitance, and mention the limitations of the Maxwell's bridge. And mention the limitations of the Maxwell's bridge. This is the discussion about the Maxwell's bridge and the limitations of the Maxwell's bridge. And also here I am trying to explain the one more topic the prevention of errors in the AC circuits. I explained with the help of one more PPT. Here the one more presentation the list the important errors they prevention in the bridge measurements. List the important errors and their prevention in the bridge measurements. The mention the limitations of the AC bridges. This is a small discussion about the limitations. On the completion of this period, we were able to know the important errors and their prevention in the bridge measurements, and mention the limitations of AC bridges, method for measurement of the small inductance and capacitances. In the previous class, we already studied about the Maxwell's bridge and measurement of the unknown inductance and limitations of the Maxwell's bridge. Here, the important errors and their prevention in the bridge measurements. The various factors causing the errors in the AC bridge circuit measurements are listed below. In the first important error is the stay inductance effects due to the imperfect insulation. The stay inductance effects due to imperfect insulation. The second is the mutual inductance effects due to the magnetic coupling between the various components of the bridge. And next one is the stay capacitance effects due to the electrostatic fields between the conductors at different potentials and residues in the component. These are the main important errors in the bridge measurement. The first one is the stay conductance effect due to the imperfect insulation. Second one is the mutual inductance effects due to the magnetic coupling between the various components of the bridge, and stay capacitance effect due to the electrostatic fields between the conductors at different potentials and residues in the components. And errors due to these effects become larger or the greater in high frequency and high voltage bridges. Therefore, some precautions should be taken to reduce the errors to a minimum. There are more important methods reducing the errors as use the high quality components. To prevent these errors, we are using some method. The first method is the use the high quality components. The good quality bridge components will normally have the advantage of high accuracy, calibration, freedom from the stay capacitance effects, and medium of the residues. That's why to prevent the errors, then we are using the bridge circuit is the use of the high quality of the components. Second one is the stay capacitance effects. If the insulation between the various components of the bridge circuit is not good, trouble may arise due to the leakage currents flow from one arm to another. This is especially true in the case of the high impedance bridges. To avoid this, various bridge components may be mounted on the insulating stands. Third one is the eddy current errors. Errors may result due to the variation in the values of standards, which may occur due to induced eddy currents in the standard components such as resistors and inductors. In order to avoid such errors, the large conducting masses should not be placed near the bridge circuit. In order to avoid such errors, the large conducting masses should not be placed near the bridge circuit. And residual errors. Through the resistors used are taken as non-inductive and non-capacitive, but their inductance and capacitance are never zero. Residual errors. Through the resistors used are taken as non-inductive and non-capacitive, but their inductance and capacitance are never zero. Residues means small inherent inductance or capacitance of the resistors. So it becomes necessary to find them in order to eliminate them or compensate for errors due to this. Frequency and waveform errors. In case of bridge network whose balance equation involves frequency, the variations in supply frequency very important both from the point of view of balancing and evaluation. This is difficult to overcome by using the filters which eliminate the unwanted harmonics from the source. The Wagner ground connections. The Wagner ground connection is used to eliminate the stay capacitances and use of insulating strands. The errors due to stay conductance is imperfect insulation can be minimized by using the high grade insulation and mounting the bridge along with the operators on insulating stands. Avoiding the conducting masses near the bridge. In order to reduce the errors due to eddy currents, the presence of large conducting masses near the bridge circuitry is avoided. Use of wave filters. Errors due to supply frequency and harmonics in the supply waveform can be eliminated by using the wave filters. The main error is because of limiting error of the known resistances, hence when very precise resistance are required having the tolerance of 1% or even 0.1%. And mention the limitations of AC bridges method for measurement of small inductance and capacitance. A perfect balance can be obtained only if the capacitors are free from the dielectric losses, that is, when air capacitors are used. Here, the limitation is a perfect balance can be obtained only if the capacitors are free from the dielectric losses, that is, when air capacitors are used. Because of frequency sensitivity, the Wien bridge may be difficult to balance unless the waveform of the applied voltage is sinusoidal. The bridge cannot be used for high resistance measurements. Similarly, heating effects due to large current also plays the major role. The resistance used must be very precise, having tolerance of 1% or 0.1%, hence the cost is high. That is the important errors and their prevention in the bridge measurements. And mention the of AC bridges method for measuring of the small inductance and capacitance. This is the topics I covered. One small quiz related question. A Wagner ground connection is used to eliminate the stay capacitance. Here answer is stay capacitance. Errors due to supply frequency and harmonics in the supply waveform can be eliminated by using the wave filters. And the frequently asked in the examination, list the four important errors, their prevention in the bridge measurements. Mention the limitations of AC bridges, method for measurement of small inductances and capacitances. These are the topics the prevention and the limitations of the AC bridge circuit. I hope all of you understood the two topics, like the measurement of inductance using the Maxwell's bridge and important errors and the prevention of the bridge measurements and the limitations of the AC bridges and the method for measurement of small inductance and capacitances. and also we discussed about the limitations of the Maxwell's bridge circuit. Okay, thank you. Have a great day.